Okay, welcome everyone. So now that we have defined what it means for a scalar to be an eigenvalue of a matrix, let's take a look at an example. So in this example, we want to show that the scalar lambda equals 4 is an eigenvalue for the matrix A, which is first column 0, minus 4, and second column minus 2, 2. So you have a square 2 by 2 matrix A. I'd like to verify that lambda equals 4 is an eigenvalue of this matrix. So by definition, we say that lambda equals 4 is an eigenvalue of matrix A if we know that the equation A times x equals 4x has a non-trivial solution. So there exists some non-zero vector x, which is a solution to this equation. So let's see how we can verify that 4 is going to be an eigenvalue of this matrix. So I could take this equation from the definition of an eigenvalue, and I'm going to subtract 4x from both sides of this equation. So that's going to leave the 0 vector on the right side. And on the left side, I have this vector matrix equation, ax minus 4x is equal to the 0 vector. So now we can represent this multiplication of vector x by the scalar 4. This would be equivalent to multiplying vector x by a 2 by 2 matrix with 4s on the diagonal and 0s along the off diagonal. So you can verify that if I take x1, x2, and multiply on the left by this matrix 4, 0, 0, 4, we would wind up with the vector for x1 for x2. So it's going to be equivalent to multiplying vector x by the scalar 4. So here I've put a subscript 2 to denote the identity, the 2 by 2 identity matrix. So again, multiplying x by the scalar 4 is the same thing as multiplying x by the diagonal matrix, which has 4s on the diagonal and 0s off the diagonal. And this is going to be convenient for trying to simplify this equation. So we have that ax minus 4x should equal 0. And now we're going to replace the 4x with 4 times the 2 by 2 identity matrix times vector x. So I can rewrite this as the matrix A minus the matrix 4i times the vector x. I can factor out an x from the right of both of these products. And so we want to solve when is A minus 4 times the identity matrix times vector x equal to the 0 vector. So does this have a non-trivial solution? So let's plug in our values that we have here. So we're going to set up this equation A minus 4ix equals the 0 vector. So the first thing that we'll do is simplify the left side. So I have, here's matrix A, 0 minus 4 is the first column, minus 2, 2 is the second column, and I'm going to subtract from it 4 times the identity matrix. So that's this matrix with 4s on the diagonal and 0s on the off diagonal. And calculating this difference of these two matrices, this would give me minus 4 minus 2 minus 0 gives me minus 2. I have a minus 4 over here. And then I take 2, subtract 4 from it, and that gives me minus 2. So basically what we're doing is taking this matrix A, and we are subtracting 4 from the diagonal entries. And that's where the minus 4 and the minus 2 come from. And we don't do anything to the off diagonal entries of our matrix A. So now we've got a matrix equation that we would like to solve. So let's take a look at that solution. So now we see that lambda equals 4 is going to be an eigenvalue of this matrix A as long as this matrix equation, which is minus 4 column 1, minus 2 in column 2, times vector x equals the 0 vector. If this has a non-trivial solution, then 4 is an eigenvalue. If the only solution to this equation is the 0 vector, then 4 would not be an eigenvalue. And so from this, hopefully you can verify that doing a replacement on row 2, subtracting row 1 from row 2, we get a row of zeros in the augmented matrix. So this matrix -4, -4, -2, -2, 0, 0 is the augmented matrix of this homogeneous equation. And we can represent it in a reduced row echelon form. And when we do so, we can see we have a free variable. x2 is a free variable. So we actually get the solution set that x1 is equal to -1/2 x2, and x2 is free. So x2 can be anything. So we could rewrite this solution set as any vector x, which is equal to some scalar times the vector -1/2, 1. And so since a non-trivial solution exists to this equation ax equals 4x, then we know that 4, by definition, is an eigenvalue of this matrix. And we actually have found an eigenvector for the eigenvalue 4, namely the vector -1/2, 1, is an eigenvector. But this is not unique. We have many different eigenvectors. So in fact, any scalar multiple of this vector v that we pick, so for example, picking x2 is equal to 2, and scaling this by a factor of 2 gives us a vector -1, 2. And this is also going to be an eigenvector for the eigenvalue lambda equals -4. So we have a whole collection of eigenvectors for the eigenvalue equals 4, lambda equals 4, and we'll see that this collection of vectors actually forms a subspace of, in this case, R2. Okay, so to wrap up this video, let's generalize the process that we just observed with the previous example. So by definition, a scalar lambda is an eigenvalue of matrix A if there is a non-trivial solution x to the equation ax equals lambda x. And what we saw on the previous example is that this condition that we get from the definition is equivalent. We can rewrite this equation as a homogeneous matrix equation and then use techniques that we've already studied to solve those equations. And that homogeneous matrix equation is A minus lambda times the identity matrix times this vector x equals the 0 vector. And provided this homogeneous matrix equation has a non-trivial solution, that would tell us that lambda is an eigenvalue and the non-trivial solution is an eigenvector associated to that eigenvalue. So the set of all possible solutions, because we've seen that once we get one non-trivial solution, we have an infinite number of solutions. And so the set of all solutions to this matrix equation A minus lambda I times x equals 0 vector, that is called the eigenspace of matrix A corresponding to the eigenvalue lambda. So for this example, for the matrix that we just looked at, we found that lambda equals 4 is an eigenvalue, and the eigenspace would be the set of all vectors that look like some scalar t times the vector -1, 2. So we have a whole line of eigenvectors associated to this eigenvalue of 4.